In this video, we are going to talk about subsequences. First, we'll review the definition of convergence and also the monotone convergence theorem. Then we'll talk about subsequences and related theorems. Next, we'll talk about limit superior and limit inferior and other notes and theorems. And then finally, we will talk about unbounded sequences. First, a quick review of the definition of convergence. A sequence, Sn, is said to converge to the real number s, provided that for every epsilon greater than 0, there exists a natural number capital N, such that for all natural numbers little n greater than or equal to capital N implies that the absolute value Sn minus s is less than epsilon. And also we had the monotone convergence theorem that said a monotone sequence is convergent if and only if it is bounded. I am also going to mention that a sequence of real numbers is said to be a Cauchy sequence if the terms in the sequence get closer together as n becomes large. And there's this Cauchy convergence criteria theorem that says a sequence of real numbers is convergent if and only if it is a Cauchy sequence. Now, I don't believe we're going to be using Cauchy sequences in this video, but since I was reviewing, I'm just going to put these two definitions out there as well. So you may have a good intuitive notion of what a subsequence of a sequence would be, but we're going to look at the formal definition and make sure that the notation sits well with you and that you're comfortable with it. So subsequences, let's say we have a sequence Sn, and the index for n goes from 1 to infinity. We're going to also look at this sequence nk, which starts at k equals 1, and it's any sequence of natural numbers such that n1 is less than n2 is less than n3, etc. Then the sequence snk, and going from 1 to infinity, is called a subsequence of Sn. The way I like to think of this notation Snk, when we have a sequence, we might use a formula. So we might say S sub n is equal to 1 over n. So really what we're doing is for each value of n, each natural number, we have this function from n to our Sn. And I could have, at some point, we had discussed this when we were talking about sequences. We could have used this function notation, S sub n is equal to 1 over n. And that would have been the same. So in this Snk, that is essentially S sub n of k. So we'll do a couple of examples and we'll look at this notation. Let's let an be our sequence. So when an is equal to 1 over n. So when n is equal to 1, we have 1. When n is equal to 2, we have 1 half. When n is equal to 3, we have 1/3, etc. Now we're going to look at nk. This is our sequence of natural numbers, and that's what's going to pick out which terms of an we're going to consider for our subsequence. So let's say nk is equal to 2 to the k. So when k is equal to 1, we get 2. When k is equal to 2, we get 4. When k is equal to 3, we get 8, etc. Now this is going to tell us which terms from here we are going to pick out. In other words, our ank, our subsequence then, is going to be a of n of k. So here, plugging in k equals 1, 2, 3, 4, 5, etc. I have an1, an2, an3, etc. n1 is equal to 2, n2 is equal to 4, n3 is equal to 8. So my sequence is going to be A2, A4, A8. My subsequence is A2, A4, A8, which is 1/2, 1/4, 1/8. With this example, I'm trying to illustrate how I like to think of this Snk term. So the nk is a function that tells me which terms of my subsequence, not terms, but which elements of my subsequence I want to pick out of my sequence S. So I have a formula here, 1 over n, to generate my sequence S, or A, and then I have my formula nk to determine which of these elements to pick out to form a subsequence A and K. My next example, I look at Vn is equal to 1/2, 1/4, 1/3, 1/5, 1/6, and that is not a sequence since the order of the terms is not preserved. In other words, over here, the 1/3 comes before 1/4, but in the subsequence, 1/4 comes before 1/3. These two terms are reversed. Since order is not preserved, this is not a subsequence, and in particular, you wouldn't be able to find an NK that would give you this reversal of terms. I have a couple more examples of subsequences of AN. Here we can pick out 1/5, 1/6, 1/7, 1/8. That would be a valid subsequence. Or we could pick out 1/2, 1/4, 1/8, 1/16. That's a subsequence. Vn is 1/3, 1/2. Already it's not a subsequence because we have not preserved the order. For our first example, we're going to look at nk. It's going to be a sequence of natural numbers such that nk is less than nk plus 1 for all natural numbers k. We're going to use induction to show that nk is greater than or equal to k. And I'm going to start by renaming nk to aj because I like to use the variables n and k as variables in my inductive proofs. However, I am going to mention that this nk was not chosen to be evil. I didn't choose this at all. This is from a book. But it was not chosen to be evil and confuse inductive proofs, but it was chosen because it is this set here for a subsequence. We're going to use this result in a theorem soon, right after this example. And it's a theorem about subsequences and the nk here. So this nk plays the role here in subsequences. Anyway, but for now, for my inductive proof, I'm just going to swap it to aj. So I rewrote this statement using a and j. So that what I have is let aj be a sequence of natural numbers such that aj is less than aj plus 1. It's increasing. And I'm going to use induction to show that aj is greater than or equal to j. So I want to prove an is greater than or equal to n for all n in the natural numbers. And I start with my base case, n is equal to 1, that a1 is greater than or equal to 1. And this is true since here we said that we're dealing with a sequence of natural numbers. My next step is my inductive hypothesis, which is assume for n equals k, that is ak is greater than or equal to k. And last, I need to show for n equals k plus 1. And I'm going to start with my inductive hypothesis, which ak is greater than or equal to k. And ak plus 1 is greater than ak. That's given because our sequence is increasing, which means that ak is greater than k, since ak is greater than k. And then that means that if I add 1 here, I can put that ak is greater than or equal to k plus 1. And again, because we're talking about natural numbers k and natural numbers in the sequence. And that's the end of my proof. Because this result is useful for other theorems, I put that result here, both in my overview slide and also in many of my notes that I have for your reference. Our next theorem says that if a sequence Sn converges to a real number S, then every subsequence of Sn also converges to S. For the proof, what we have is the limit of Sn. Since it converges, we're going to call the limit S. And we're going to let nk be a subsequence of natural numbers such that n1 is less than n2 is less than n3. So we want to show the limit of Snk is also equal to S. If you recall from our chapter when we talked about convergence of a sequence, we had this strategy where we looked at Sn minus S and then we solved for n in terms of epsilon, but we won't be able to use that now because we used that strategy when we had a formula for Sn, a formula such as Sn is equal to 1 over n. Here we don't have a formula for Sn because we're just talking about sequences in general. So what we need to use is the definition of convergence, and the other thing we're going to use is the results of this example here, because nk, that is the function that tells us which members of our sequence we're going to pick out, nk is a sequence of natural numbers that is strictly increasing. So the other thing we are going to use in this theorem is the fact that nk is greater than or equal to k. As I mentioned, we're going to start with the definition of convergence. So given an epsilon greater than 0, since Sn converges, that means there exists, or we can find a natural number capital N such that if any natural number little n greater than or equal to capital N, then the absolute value of Sn minus S is less than epsilon, straight from the definition of convergence. And again, we're using the fact that the sequence converges to a real number S. The next thing we're going to do is we're going to choose a k greater than n. And remember this big N, that's where our sequence is within this small, tiny epsilon of our limit. So k is going to be greater than n, so we're going to be within our limit, our epsilon. And again, because we're using this capital N from the line above, then nk is going to be greater than k, using the results of our example, which is greater than capital N. Using the results from the previous example here, nk is greater than k. So what we have is nk now is the function that is picking out the terms from our sequence. And nk, we're going to start with nk greater than n. So that means snk minus s is also within epsilon, because we're going to pick out the nks that are greater than n, which means if snk minus s is less than epsilon, that means the limit of snk is also equal to s. Here we have an example using this theorem that if a sequence converges to a real number s, then the subsequence also converges to s. So suppose we have x between 0 and 1, and Sn is equal to x raised to the 1 over n. We're going to find the limit using this theorem above. And first we're going to use the monotone convergence theorem, which I have up here for your reference, to show that Sn converges. To use the monotone convergence theorem, we need to show two things. One, that the sequence is in fact monotone, increasing or decreasing. In this case, it's increasing. And then we also need to show it is bounded. We are going to start with bounded. Since x is between 0 and 1, that means x raised to the 1 over n is also between 0 and 1. Therefore, x raised to the 1 over n is bounded. Next, we need to show that Sn is increasing. To show it is increasing, we need to show that Sn plus 1 is greater than Sn. And plugging in for Sn plus 1 is equal to 1 over x raised to the 1 over n plus 1, and Sn is x to the 1 over n plus 1. So this is what we need to show here, that x raised to the 1 over n plus 1 is greater than x to the 1 over n, which I have done on this next line. I move this term over with subtraction, and then I combine these two terms, and I see since x raised to this power is less than 1, then this subtraction is going to be greater than 0 for all natural numbers. Thus, that must mean that the Sn plus 1 is greater than Sn, and by the monotone convergence theorem, since we have an increasing sequence that is bounded, then that must mean our sequence converges. We are going to consider the subsequence of s to the 2n. So s2n is equal to 1 over x raised to the 1 over 2n, which is x 1n raised to the 1 half, which is just Sn to the 1 half. By the theorem, we said that every subsequence is going to converge to the same thing the sequence does, so the limit of s2n should equal to the limit of Sn. We will use the fact that the limit of Sn to the 1 half is equal to the limit of Sn all raised to the 1 half. So s is equal to the limit of Sn, which is equal to the limit of s2n, again, because the limit of the subsequence is the same as the limit of the sequence. And the limit of s2n is the limit of Sn to the 1 half, which we have from this line, which is equal to, and using this fact here, limit of Sn to the 1 half, which is also equal to the limit of Sn raised to the 1 half, which is equal to, well, the limit of Sn is equal to s, so that's equal to s to the 1 half. And looking at this algebraically, we have s is equal to s to the 1 half, or s squared is equal to s. So that means s is equal to 0 or 1. but S1 is equal to x, which is greater than 0, hence s is equal to 1, and the limit of x to the 1 over n is equal to 1. And this is kind of what you would expect, since 1 over n approaches 0 as n gets very large, so x to the 0 would be equal to 1. But of course, in this class, it's important you know how to use these theorems to derive it using theorems. Next, we're going to show Sn is equal to negative 1 to the n is divergent, again using that same theorem. And we're going to do this by contradiction. So if Sn equals negative 1 to the n were convergent to some number s, then every subsequence would also converge to s. But s to the 2n converges to 1, and the odd s to the 2n plus 1 converges to negative 1. And since limits are unique from a theorem from the last video, we conclude that negative 1 to the n diverges. Our next theorem is every bounded sequence has a convergent subsequence. To prove this theorem, I'll need some space because I'll be doing some drawing. So I kind of condensed the notes I have on top for reference, and I moved it up. Here's the theorem. And for our proof, we're going to assume a bounded sequence because that's the start of our theorem. And then we're going to construct a sequence that has a limit. That is, we're going to construct a convergent subsequence. We will start by naming our bound sequence as Sn, and we'll say that it is bounded by capital M. So Sn is going to be an element in the closed interval negative m to m, and we'll split up our closed interval into the union of two intervals, negative m to 0 and 0 to m. So Sn is an element of the union of these two intervals here. There are infinite many elements Sn, essentially because we have Sn defined for n all natural numbers, but we have formally stated it here. If there are infinitely many Sn, that means either the interval minus m to 0 or the interval 0 to m, or perhaps both have infinitely many terms. Either way, we're going to choose one of the intervals with infinitely many terms, and if both of them have infinitely many terms, we just choose one at random, and we're going to call that interval I1. So for example, I1 might be the interval 0 to m. Next, we will pick one of the Sn terms from I1, and we will call it Sn1. Now we're going to take I1 and split it into two equal parts, and we will pick the part with infinitely many Sn. So I'll call that I2, and we are going to pick Sn2 from I2. And we are going to repeat this process until we have constructed the sequence Sn1, Sn2, Sn3 up to Snk. Before we continue with this proof, I'm going to draw some pictures just to get a better feel for this subsequence. So we have this infinite sequence Sn. It's bounded by m, so the absolute value is less than m. So here I have on my real number line negative m and m. So all of my sequence is in here. I'm going to create a subsequence, and the way I do that is I divide my interval negative m to m in half. So I have my interval negative m to 0 and 0 to m. And between these two intervals, I'm going to choose one that has infinitely many members of the sequence. And for the sake of argument and without loss of generality, I'm going to choose 0 to m, and I'm going to call that interval I1, and from the interval I1, I'm going to choose one of my infinitely many Sn, and I'll call that Sn1. So that Sn1 will be the first element of my subsequence. To get my next element, I'm going to take I2 and I'm again going to divide it in half. And then I'm going to choose half that has an infinite number of members. And just to be different, this time because on I1 I chose the interval on the right. For I2, I'm just going to choose the interval on the left. But again, I have to be sure that this has an infinite number of members. And so from I2, then I'm going to choose an element, and I'll call that Sn2. So Sn2 is within this interval here. So now I have two elements of my subsequence. I repeat this for I3. So I take I2, I divide it into half. although this doesn't look like half, but pretend like it's half. And then I choose the one with an infinite number of members, and I'll choose I3, and from there I'll take one of the SNs and I'll designate it as SN3. So now I have a subsequence SN1, SN2, SN3, and I continue this process. At this point, there's one more picture I want to show you, just because it looks like this isn't converging, but it really is. So you might want to graph it here, or, well, it's not really converging, but it could be. So the idea is on your real number line, this is my real number line with values from m to negative m. This plot here is n, and so what I'm going to plot is Sn. So for I1, remember I1, I chose the top half of my interval negative m to m. So I1 is 0 to m, and I chose Sn1, which was sort of almost at the middle of my interval, so something like this. Then for I2, now remember I2 is half of my I1, and in this case it's the lower half of I1, and I chose something a little bit less than half. So here it is, more or less. The blue dot is Sn2. And then the last interval I drew was I3, and remember I3 is half of I2, and in this case I chose the upper half, and then I have something a little greater than half of the interval, so something over here, more or less, is my green dot is Sn3. So you can see my subsequence is sort of here, and what we're going to show is that it does converge. So here you should have a good sense of how we're constructing our sequence. And one other note, so each of the intervals, I1 contains I2, which contains I3, right? Because I1 is this bigger interval, and then I2 is half of I1. So each of them are contained in the previous, or all the previous intervals. And one last note, the length of IK is equal to m divided by 2k minus 1, because each time we do an iteration of IK, we're having the length of our interval. Now that we've constructed a subsequence of Sn, we need to show that that subsequence, what is it that we're trying to prove, has a limit, that it is convergent. So what we are going to do is take L to be the intersection of all of our IK. So if we keep getting smaller and smaller, eventually we're going to have intervals that are really tiny, and then if we do that up to k equals infinity, eventually we're going to approach L, which we're going to claim is the limit of Snk. I have condensed our process for finding our subsequence, and I have our claim here. If we take L from the intersection of all of our IK, our claim is that L is going to be the limit of our subsequence, and therefore, from our theorem, is also the limit of our sequence. To find what it will take to prove that the limit L is equal to Snk, we have to look at our definition of convergence and limit, and what we have to show is for every epsilon, that every Sn minus L is within that epsilon. So what we're going to do is use these I sub k's to find our epsilon. And the reason why we're using I sub k's is because our I sub k's are getting smaller and smaller, and yet our subsequence is staying within the smaller I sub k's. So in other words, if epsilon is large, let's say epsilon is equal to m, right? Then of course we're going to capture everything in the subsequence because, well, the whole sequence is bound by m. And then if we know that there's still an infinite amount of the sequence in just the upper half of this interval, instead of looking from m to negative m, we can take a smaller interval, so like another smaller epsilon, and we can see that our infinite sequence is still staying within that smaller epsilon. So the smaller the epsilon gets, the smaller the larger k will get, because you're looking at smaller and smaller intervals that's bounding your sequence. So that's the idea of using the I sub k. So our proof is going to start, given epsilon greater than 0, we're going to take k to get the interval ik such that m divided by 2k minus 1 is less than epsilon. And remember, this m divided by 2k minus 1, that's the length of our interval. And that we're going to set the length of our interval less than epsilon. And said another way, when we're solving for k, we want 2k minus 1 is less than epsilon over m. But now when we consider two elements from ik, when we consider the limit, which is in ik because that's how we found L, as we took it from the intersection, and then any other element of the subsequence, Snk, is going to be in the interval. And Snk minus L is going to be less than epsilon, which means, by definition of convergence, limit of Snk is equal to L. And because if a sequence converges to a real number, then the subsequence also converges to the same limit. That means the limit of Sn is also equal to L. And that concludes this proof. Our next theorem is every unbounded sequence contains a monotone subsequence that has either positive infinity or negative infinity as a limit. This theorem seems intuitive enough, and I might have skipped this proof, except it's fairly short. So we're going to do the proof. We will start by naming our unbound sequence Sn. It's unbound above, and we are going to construct an unbounded increasing subsequence of Sn. Since Sn is unbounded above, that means given any real number m, there has to be terms, infinitely many terms, larger than Sn. And if that weren't true, then m would be a max. So it's unbounded, so we have infinitely many terms of Sn larger than m. In particular, for m is equal to 1, we know there's an Sn1 greater than 1. And this fact comes from this exercise we had done previously. We also know there's an n2 greater than n1, because this is how sequence works. So we have Sn2, and we'll take that to be the maximum between 2, since Sn2 is going to be greater than 2, and Sn1. In general, given n1 through nk, all the indices for our sequence, our subsequence, nk plus 1 is greater than nk, such that and then we'll set Snk plus 1 equal max of k and Snk. So it follows that Snk then is unbounded and increasing, and by the limit theorem, Snk equals positive infinity. We can deploy a similar argument to produce an unbound decreasing subsequence having a limit equal to negative infinity. Our next topic is of limit superior and limit inferior. And this is an important topic because we're talking about sequences and convergence of sequences, and many sequences do converge. But what do we do for those sequences that don't converge, that don't have a limit? Well, it turns out every bounded sequence has a limit superior and limit inferior. Again, every bound sequence has a limit inferior and a limit superior. So first we have this definition, which is a little bit complicated. I'll read it to you, and then I'll give you some intuition or some drawings to kind of illustrate what this definition is, and then we'll come back again and look at the definition one more time. So for a bounded sequence Sn, a subsequential limit of Sn is any real number that is the limit of some subsequence of Sn. If S is a set of all subsequential limits of Sn, then we define the limit superior or upper limit of Sn to be lim sup Sn equals sup of S. And again, S is a set of all subsequential limits of Sn. Similarly, we can define limit inferior or lower limit of Sn to be lim inf of Sn equals inf S. I'm going to start by saying intuitively lim sup is the long run, and I have this in quotes, sup of Sn. Let's take the example S1 equals 4, S2 equals 3, S3 is equal to 2, S4 is equal to 1, S5 is equal to negative 1, S6 is equal to 1, S7 is equal to negative 1, and from here on out, it just oscillates back and forth between negative 1 and 1, and I plotted these points here on a graph. This sequence does not converge, but in the long run, for n greater than or equal to 4, the sup of the subsequence of Sn, n greater than or equal to 4, is equal to 1. And this is what we would call the lim sup of Sn is equal to 1. Let's consider some of these subsequential limits of Sn. So a subsequential limit, remember, is a limit of some subsequence of Sn. So let's take the subsequence S2n. So that would be S2, S4, and S6, the even numbers. So what we would have for S2, we'd have 3, and then S4 would be 1, S6, S8, those will all be 1. So the limit of this subsequence is equal to 1. If, on the other hand, we looked at S2n plus 1, that's the subsequence of odd numbers, S3, S4, S5. So S3 starts at 2, S5 is negative 1, S7 is negative 1, and we continue, and they're all negative 1, which means the limit of S2n plus 1 is equal to negative 1. And then looking at our definition of limit superior, or upper limit, then the limit of lim sup of Sn is equal to the sup of S, where S is the set of all your subsequential limits. So you can see eventually all your subsequences are going to end up with either a 1 or a negative 1 as the sup. So the lim sup of this series, Sn, is the sup of 1 and negative 1. Again, it's this. It's the sup of S, where S is your sups of all your subsequences. So what subsequences, sorry. So lim sup of Sn is sup of 1 and negative 1, which is equal to 1. Similarly, lim inf would be equal to negative 1. And so this is our definition of limit superior and limit inferior. For bounded sequence, Sn, and remember, currently we are working only with bounded sequences, a subsequential limit of Sn is any real number that is the limit of some subsequence of Sn. So if S is the set of all these subsequential limits of Sn, then the limit superior or upper limit of Sn is the sup of S. And similarly, we define limit inferior. Two other notes. Since the limit superior or inferior requires a bounded sequence, we are guaranteed a convergent subsequence, and that's by this theorem here. So, which is that every bounded sequence has a convergent subsequence. So the set of subsequential limits will be non-empty and will be bounded. Then the completeness axiom will then imply that sup S and inf S will both exist as real numbers. The second note is the limit of the inf of Sn is always less than or equal to the limit of sup of Sn. And if Sn converges to S, then the limit of the inf of Sn will equal the limit of sup of Sn, which is equal to S. And if the limit of inf of Sn is less than the limit of sup of Sn, then we say Sn oscillates, like the previous example where we were oscillating between 1 and negative 1. Here is another example. So if Sn is equal to negative 1 to the n plus 1 over n, what are the first 7 terms of the sequence? What does it seem to converge to? What does the subsequences S2n and S2n minus 1 seem to converge to? And what is sup n and inf n Sn? Here I plugged in n equals 1 through 7 into Sn to get the first 7 terms of this, and we can see that this is oscillating between positive and negative numbers. I have pulled out S2n minus 1, and it looks like we're converging on to negative 1. When I look at my S of 2n, that looks like it converges to 1. So the sup of Sn is equal to 1. Since we're oscillating between 1 and negative 1, the sup is 1, and the inf of Sn is equal to negative 1. Another theorem, let Sn be a bounded sequence and let M equal lim sup Sn, then the following properties hold. For every epsilon greater than 0, there exists a natural number capital N, such that n greater than or equal to capital N implies that Sn is less than m plus epsilon. And then B, for every epsilon greater than 0 and for every natural number I, there exists an integer k greater than I such that Sk is greater than m minus epsilon. Furthermore, if m is a real number satisfying properties A and B, then lim equals m is equal to lim sup Sn. The picture I have for this theorem is down here. So I have M, that's our limb sup. Remember, the limb sup is the supremum of all the limits of subsequences of Sn. So here we have M, our limb sup, and then we look at M plus epsilon and M minus epsilon. So let's first consider M plus epsilon. So there can only be finitely many terms that are greater than M plus epsilon, because if there were infinitely many terms, then these terms would have a limit greater than M plus epsilon. But since M is the sup, that's not possible. On the other hand, if we consider M minus epsilon, there must be infinitely many terms greater than, because we have to be able to reach an upper bound of M. And this also suggests you can get arbitrarily close to M. Then we have a corollary to the theorem. Let Sn be a bounded sequence and M is equal to limb sup of Sn. Then M is an element of S, where S is a set of subsequential limits of Sn. That is, there exists a subsequence of Sn that converges to M. And here we have another example. We have Sn written here and also here. We want to find the set S of subsequential limits, and then we want the limit superior and limit inferior. I divided this into 3 subsequences, so this was sort of, I don't know, looking at it, trial and error. So I could see this blue sequence seems to be going, and it's every third one, seems to be approaching 0. So I underlined my 0 in blue to remind me that this blue sequence is going to 0. I have this yellow sequence here. Sorry, it's hard to read where the lines are, but I also underlined them, every third one, and that seems to be approaching 1. And then my green sequence I have underlined, and that seems to be approaching -1. So my limb sup is the maximum of S, my sup of S, which is 1, and my limb inf is equal to -1. And we have another theorem. Suppose that Rn, and this is really, we're almost at the end. Suppose Rn converges to a positive number R, and Sn is a bounded sequence, then the limit of sup of Rn Sn is equal to R. Remember, that's what Rn is converging to, times limit of sup of Sn. Our last topic is really quick, and there is one example after the definition, unbounded sequence. So if Sn is unbounded above, then the subsequence having positive infinity is its limit, and as we would expect, we define limb sup equals positive infinity. Here is the definition that we've been talking about, where sup Sn is the supremum of the set of all subsequential limits. And last, if no subsequence converges to a finite number, we have limb Sn is equal to -infinity. And our last example is of unbounded sequences. So let Sn equals n times sine squared n times pi over 2. Find the set S of subsequential limits and the limit superior and limit inferior. So you can plot this, but I was too lazy to. But what I do realize is this is cyclic, and so you can get 0. You can pick out the elements of the sequence to give you a subsequence that's always 0. And the other thing is, here it's cyclic, but since you're multiplying n, and n constantly increases, your upper limit is positive infinity. So in this case, our limit superior is going to be infinity, and our limit inferior is going to be 0. And that is it for our material, and so we're ready for some review problems. I have 3 problems for you to try. Pause the video, give them a try, and on the next slide I'll have solutions. Here are the solutions. And that's it for this video. Thank you for watching.